Okay, now we are switching over to the fifth talk of 6 in this section. Title is Funshade, Function Secret Sharing for Two-Party Secure Threshold Distance Evaluation. And Alberto is giving the talk.
Thank you very much. Can you hear me well? Not sure if it's so. Okay. So I just need to talk that way. So hello everyone. My name is Alberto Ibarrondo. I'm going to present you today our joint work with Melecon and Japan, Funshade, Function Secret Sharing for Two-Party Secure Threshold Distance Evaluation. It's a bit of a tongue twister, but it makes sense. The goal of the work that I'm presenting here is quite straightforward. We want to evaluate the following function. A function that takes two inputs being two vectors, the vectors x and y, and you want to evaluate the scalar product of those vectors, and then a comparison of the result with a given threshold, theta. And we're going to set this in a scenario where we have two parties. I want to do it privacy-preserving. We want to evaluate it in a privacy-preserving manner. I want to do it efficiently. As we said, we are targeting distance evaluations in the title. In our paper, we consider multiple distance evaluations more than just a scalar product, and we're doing it against a fixed threshold that we set at the very beginning of the protocol. In a 2PC scenario, where we consider an Alice and a Bob playing the roles of the two parties, we're going to be having each party giving or inputting their own vectors. So we're going to have the vectors x and y. And we want the protocol to output, as we said, for either Alice or Bob, that's the choice we can have, the result of this computation. With the following security conditions. We want Alice not to have to reveal the vector x, and we want Bob to not have to reveal the vector y. And we want to be doing so in a privacy-preserving manner, such that Alice and Bob will be following the protocol faithfully, that is, we're in the semi-honest domain, guaranteeing input data privacy. The application that we're targeting for this work is that of biometric authentication. I'm going to be showing you now the use case of flight boarding control, but it could be applied to basically any other scenario where you have the same constraints of two parties and such. So let's picture it out a bit more in the scenario. We have a set of users, and we're going to have the two parties that would be the equivalent of Alice and Bob in our setting, a biometric provider, and the gate. In the enrollment phase, so when the user buys his plane ticket, the user is going to give his biometric information to the biometric provider to be securely stored. And then once the user actually wants to go into the airport and go through the gate to board the plane, the gate is going to capture his live biometric information, the vector x, and together the biometric provider and the gate will jointly compute this function going through our protocol to finally obtain a result that would be either a match or a reject. If we get a match, then we are able to fly. So good. How do we achieve this? We're using two building blocks. We're an MPC, first of all, so we're using MPC-based building blocks. The two building blocks that we use are additive secret sharing for additions and multiplications, and we'll be using function secret sharing for the nonlinear operation, that is the comparison. The additive secret sharing, though, will have a small twist to it. We've already introduced MPC widely in this conference, so there's no need to go beyond that, but it's just a collaborative computation of whatever mathematical function we feel like, with the idea of divide and conquer. Going a bit more into secret sharing, and in the 2PC scenario, just to get our ideas very clear in mind, we have Alice and Bob splitting a secret that is a secret shared between them into shares x0 and x1. And we know of the technique that is called Beaver multiplication triples from a seminar work more than 20 years ago that allows you to generate correlated randomness in a setup phase such that you have the secret shared value C equals the multiplication of the secret shared values A and B. In fact, the twist that we're using in this work comes from a previous work that is called ABY 2.0, and we're naming it Pi secret sharing for the following reason. It's still a secret sharing scheme, additive secret sharing scheme into party computation, but the twist is that we have a third share, this capital delta X, that is going to be that is public, or that rather both parties know about it, whereas the two small delta shares, delta x0 and delta x1, are kept private to each party. The advantage of using this technique is that, in fact, when we pre-compute Beaver multiplication triples, we can tie the result of the Beaver multiplication triples to the inputs that we're later going to be using. So this delta x0 and this delta x1 that you get at the very bottom are actually tied to the delta x0 and delta x1 of our secret sharing scheme. And we will see why this is so interesting for us. In order to compute a scalar product, that would be the first step for computation, we would be performing the setup for the Beaver triples. We would secret share our inputs. And first, we would blind each of the input elements with our Beaver triples. Then we would open these blinded results, D and E, respectively, and reconstruct them. And lastly, we would perform a local cumulative addition to obtain the shares of our result Z. We would just need one extra round of communication so that we could get the final result Z equals X times Y. In the case of bicycle sharing comparison, we would just need one local round of addition, cumulative addition, plus that final round of communication. And that is where the interest comes from. We're actually removing the need of that first round of communication from before. And very importantly, what we're going to see here, we have local cumulative addition and then one round of communication. We're going to see why this is so important and how this plays off with our next step in the protocol. We're using functional secret sharing, as I said, to perform comparison. As opposed to secret sharing in general, in FSS, we're applying a public input X on a private shared function F, such that the pieces of the shares of Fi, when you add them together, applied to that same point X, you obtain the final result F of X. And we are applying this to the comparison function, as we said. This is the way it would play out. First, we would need to create some random mask in the setup and generate the FSS keys tied to it. This mask, we need it so that we can preserve the privacy of the input in the whole flow, so that we are computing function keys, or F shares, for the function x greater or equal than r. That's where the hiding comes from. And then this is the way the protocol would play out. You would first blind your input with R. Then you would open it by sending the shares and reconstructing the blinded value. And you finally locally evaluate the FSS shares with your blinded input. To obtain finally the same as you would have obtained in clear text with a comparison of 0, completely removing the information about the mask that you've used throughout the protocol. Very importantly, here you can see that we have local addition and then one round of communication. If we were to get these two things together, and this is what the main idea of this paper is, we could merge the local addition and one round of communication from pi-secret sharing with the local addition and one round of communication at the input of the FSS gates. This way, we'll be obtaining a scalar product and a comparison with a very highly optimized online phase with only one round of communication that is independent from the size of the bit inputs. It only needs to send two shares, the shares of Z0 and Z1 hat, so the ones that are already blinded, that are independent from the vector length, and it achieves perfect correctness with no degradation in the numeric precision. This is the way it will play out in our biometric scenario to keep things a bit more concrete. We have our biometric provider on our gate. So the user in the enrollment phase would talk to the biometric provider to submit his reference vector that would get secret shared with PySS. Later on, in the authentication phase, the user would secret share his live vector, and both parties, the BP and the gate, would evaluate the target function to finally reconstruct the result in the final step and obtain the match or reject to decide if you fly or not. We implemented this technique and in Portable C, and the code is available online. And we tested it with multiple cases. To note that for those of you that want to implement but they are using Python, we have a wrapper in Python, and it should be very easy to use in Golang or Rust. In our tests, we run latency tests against the number of vectors that you're using in your number of vectors that you're comparing against. And so we see, just to give you one single figure, that we need around 10 seconds for matchings between 1 million vectors with 32-bit precision. And this could go even beyond that, because the results that I'm showing you here are using just one core, so there's still plenty of room for parallelization. In here, you see the percentage of the overall latency that is required for communication. After we reach around 10,000 or a bit more on the number of vectors that you're using in the database, the computation would dominate. And that means if we were to use GPUs or just multi-cores, we would certainly improve on the overall latency. And that's basically it. Just to get on some quick conclusions, we're offering a two-party protocol in the semi-honest domain to evaluate distance metrics followed by a comparison that is using additive secret sharing and function secret sharing. It is efficient because it requires just one round of communication and sending 2 ring elements in the process. It is very lightweight. We achieve 1 million evaluations in around 10 seconds. And it is open source, so we're happy to be using it and to be sharing it with the community. Thank you very much, and I'm ready to take questions.
Yeah, thank you very much. Any questions? There's one question over there. And in the meantime, please already set up your presentation laptop.
Hi, thanks for the nice talk. I was wondering about the use case. Can you maybe elaborate on the motivation behind hiding the picture taken by the gate from the biometric provider and vice versa?
So there are 2 things that you get in there. If you're hiding your live picture from the biometric provider, you make sure that the biometric provider cannot track you. So if you're going through multiple processes, or if you're using the taking different flights, the biometric provider will never get that information from you. And the other way around, actually, the most important thing is that the gates, so the airport, will not get the information that doesn't need. In the sense that you don't need to expose the information, the biometric information of the users that were enrolled, but you still get the same functionality of knowing if a user is in the list and then allowing them to go in.
The biometric provider has to provide the correct input, so it knows by providing the correct input to the protocol. It needs some identifier which X to provide, right?
Come again, sorry?
And so the biometric provider needs to input X into the protocol.
There are multiple ways to go through it. You can go in an identification way, in the sense that you could provide every single element that you have in the database as a biometric provider and test for all of the elements and see if there's any element that actually matches positively.
Okay, thanks.
Thank you.
Okay. Any further questions? You have one? Okay.
So thanks for the talk. What other method before this one? So do you know, is it existent, like this problem before, or other method that is?
So yeah, I actually didn't go too much into the comparison with previous works, but most methods in 2PC normally use techniques that are more based on numerical tricks to extract. There are at least 2 families of techniques. One that tries to convert the arithmetic shares into binary shares, and then you extract the bit of the most significant bit for the comparison, and then you go back into arithmetic. Or you do some type of numerical tricks to try to do the same thing while staying always in the arithmetic domain. The advantage of using FSS, and that's only been used in one previous work on this, well, could consider 2, is that you do get this comparison locally. And the difference with the previous work is that we managed to compress also the multiplication with this FSS gates, so that we get only one round of communication for the whole thing.
Okay, thanks.
Okay, thank you. So I would say then thanks again.
Thank you very much.